So I'd like you to imagine something, and I'll be writing on the screens now, an energy and your X. And this energy function will have some shape. And this would be an X you might observe of some material, let's call it small I. And now, after passing by a barrier, you get a new compound J. This could be a different constitutional isomer. Now, if you take some measurement, for instance, the dipole moment of one isomer, in general, it's not going to be equal the dipole moment of another isomer. I'm not obsessed with dipole moments. We could take another property. Doesn't really matter. Okay. You could take spectrum. You could take a stress tensor. You could take whatever observer you want to count. It's optical activity. It's magnetic properties. The one thing I am obsessed about, and I hope I can convince you by this little intro, that's the energy. The energy will tell you about the X. Okay? And then the X will determine the property. So what you have is P is a function of X, which is a function of the energy. Yeah. So what you observe in nature in terms of a material is always some X that locally minimizes an energy. Our goal in this course is to give you an idea of how is X linked to the various energies. And when I say that, I don't mean it lightly, I mean it in a quantitative, rigorous, physics-based fashion. So that afterwards you have a rigorous idea of how X and E are linked. And with X, we, as we discussed before, refer to the composition and the atomic structure of the system. So this is the microscopic view on X, right? It's very important for you to realize that, and you have had courses in the last term on the quantum mechanics of atoms and coordinates. You also had courses on thermodynamics, where you consider an entire bulk. Now, how are these linked? In the quantum mechanics, you've solved the energy problem. for the microscopic system. And you've started with that, right? You didn't, I know you're still very early in the field, but that's where you started out. Now, we'd like to know, how do we go from there to the energy of which you already studied in thermodynamics? So in some sense, you have the macroscopic world with thermodynamics and the microscopic with quantum mechanics. Now, this course deals with the question, how do we connect these two rigorously? Now, what's the difference, right? The difference really is that you have many microscopic worlds making up the macroscopic system. How many? Anybody? How many molecules do you have in a glass with a liquid when you experiment? It's Avogadro's number, right? So we have roughly 10 to the 23 of these guys, say 6 to the 10 to the 23. Now let's say you have a little bit more than a mole. So we say it's 10 to the 24 in your macroscopic little sample. Now it's impossible to do quantum mechanics on the entire system of 10 to the 24 times n number of atoms. That's something we cannot do. In your quantum mechanics course, you probably dealt with very few dimensions. Be 1 or 2 or 3, 10 to the 24. We don't even have a name for such a large number. So we go up to hexa, maybe. So mega, giga, hexa, tera, hexa. But there's nothing for 23, 24. But you can, it's so large, many people don't shy away from actually imagining it. But I invite you to imagine it. It's not 10 to the 24. It's not infinity, right? So this is the same as 10 to the 8, 10 to the 8, 10 to the 8, okay? So you could imagine a cube with 10 to the 8 molecules in one dimension, then 10 to the 8 in the next, and 10 to the 8 up. Right? Now 10 to the 8 is 100 million. You could imagine 100 million, I think. So imagine a cube with each edge being 100 million molecules. Now it's clear we should be doing statistics for such large numbers, but this is not infinity either, right? It's very finite, right? The world is finite. There's estimates that we have 10 to the 55 or so atoms in this galaxy. So it puts things in perspective, right? So what we do in this course is we use what's known as statistical mechanics to bridge these two worlds. Okay. And this is quite a recently introduced exercise. It's still quite modern. So the thermodynamics you've heard about predates this course by at least 100 years. And a lot of the statistical mechanics is based on Boltzmann, who only lived 100 years ago or so. So the stuff we are discussing here is quite recent. Right? Chemistry as a science is much older. So it's a relatively recent addition to our field. Are there any questions? Doesn't seem to be the case. So my plan is to cover this with the following bunch of topics. We will first have an introduction. Then we'll be discussing the partition function. Then we'll be talking about equation of states. Then we'll be discussing the degrees of freedom. And then I would like to finally, and that's sort of a glorious accomplishment of this field, we want to understand equilibrium constants. You learned about the equilibrium constant your first semester on, I think, and maybe even in high school already. It's like one of the most crucial fundamental properties in the chemical sciences. And what this topic of statistical mechanics allows us to do is to actually predict it from first principles, from quantum mechanics. We have the rigorous link between these two. Now, you can measure the equilibrium constant. You probably did. And these predictions, of course, are then to be falsified and tested. Right? And they have been. And so there's many decades of experimental evidence for these theories to actually work surprisingly well. So it's extremely encouraging, I think. Beautiful manifestation of human civilization that our understanding of nature has advanced to such a degree we are able to predict such things. Any questions? We'll start with the intro then. And in particular, I'd like to take off with our view on thermodynamics. There are three fundamental laws in thermodynamics. And I like to use this symbol, the flipped E, to denote that there is, right? It's a math symbol. So there are three laws, and these laws are actually postulates. There's no proof for them, right? It's they over the centuries, people have realized they work. Right? That's their justification. There's no other justification. So, and that's a bit similar to quantum mechanics, which also has postulates, right? Now, our goal is to link quantum mechanics to the thermodynamics. So historically, thermodynamics came first. But from our modern perspective, actually quantum mechanics comes first, right? And then we build up things going macroscopic, right, by doing the statistics. And then if we do things right, we should recover the old thermodynamics, which is known to work, right? And in particular, of course, we have the zeroth law that the temperatures of two systems are the same if these two systems are in equilibrium. The first law is that your delta U, any change in energy, is composed of a change in heat and a change in work. Which come from an external reservoir, right? So your system itself does not change its energy. The second law tells you that your change in entropy, which is a reversible heat change over the temperature, will always be larger equals 0. So the first law forbids you to make claims of a perpetuum mobile, which would change the energy without tapping a reservoir. So you could produce energy, basically, right? That's known as a perpetuum mobile of the first kind. The second kind would be the one that violates the second law. So that would be something where your entropy change would be negative. Okay. An example for that is a ship that runs by cooling down the water in the sea. So it extracts heat from the sea to run itself. We also have irreversible processes. That's why you have this inequality. It should be an inequality. And I hope you did this in your thermodynamics course. This results in the efficiency of heat engines to correspond to what Carnot derived. Did you do this in your thermodynamics course? Okay, great. So one really remarkable thing about statistical mechanics is, for example, you don't only have to believe me and wait until the end of this term to see if we can actually predict equilibrium constants. We will see earlier that you can actually derive the second law of thermodynamics using statistical mechanics and quantum mechanics. In other words, if you believe in the postulates of quantum mechanics and you follow all the derivations we do now, you will no longer need to rely on the postulate of the second law. You can simply derive it. So strictly speaking, nowadays, that's the news flash, second law is no longer a postulate. Now, the question is, what are your variables now, right? We had this variable x. That's the microscopic one. But go back in time, no, mid of 19th century. You're sitting there, you don't know anything about atoms. Right? All you have is some matter. So what are the variables if it's not x? Anybody? For example, so volume, mass, right? What is? Yes. Temperature. Yes. Beautiful. Okay. Mass, very much related to stoichiometry composition, right? Never forget in the periodic table, the nuclear charge grows as you go from left to right, but so does the mass of your isotopes. Every proton, roughly speaking, you also get a neutron. So clearly, now these were the variables. And the fantastic breakthrough in thermodynamics was to say, there's this energy function. The energy rules. Right? That's the breakthrough. There's no, you cannot measure energy. It's not an observable like that. Right? You don't see it. If you do an experiment on some matter, you don't directly get energy. You get the behavior of matter. And the idea that there is some function that controls that behavior, we call it the energy. That's a fantastic insight. So we have the energy, and what we typically study then in thermodynamics are equations of state. They do not have to be, and not necessarily energies, but most of them are. We first focus on those because of the importance of the energy, right? Now this comes from Hess law, some property which does not care how you got there. So that it's a state function. It will not depend on the path you took to get there. Now, one equation of state you're familiar with is the ideal gas law. PV equals nRT. Did you know that this is an energy? Did you realize? Who realized this? Who knew? PV, nRT, this is an energy. It's easy to see. Let's go through the exercise. What is pressure? Pressure is force over surface, some delta x square. Okay? What's volume? Volume is delta x cubed. Okay? This is force times delta x. Okay? if your force happens to be not a function of x, then this is simply the integral from some initial x to some final x of the derivative of the energy, which is the force definition. So dx of the energy. If I use some notation you're not familiar with, just stop me, okay? Don't be shy. This is my way to write derivatives, dE dx, partial derivative, okay? Now, this integral is the energy difference. This classical mechanics 101. You've probably seen this in high school. You could also look at the units of nRT. What are the units? Mole times kilojoules per mole and Kelvin times Kelvin. The moles and the Kelvins cancel. You're left with kilojoules. Now, you can take such energies and keep some of these variables fixed. And then you will get the internal energy in entropy and volume, the enthalpy and entropy and pressure, the Gibbs free energy and pressure and temperature, or the Helmholtz free energy in volume or temperature, right? And we can expand du in the entropy and the volume. And then analysis tells you, thermodynamics tells you the slope of the energy with respect to entropy, right? That's my temperature. And how my energy responds to volume changes, that's my pressure. And so this is T ds minus P dV. This is actually sign convention. That's one of the incredible equations in thermodynamics. So it took humanity ages to get to this insight. It's really I don't think it's stressed enough that this formed the basis for the Industrial Revolution. You cannot do steam engines without this. And whatever happened in terms of civilization progress in 17th, 18th, 19th century, it was all steam engines. So our modern civilization would not exist without this. It's quite clear. A lot of this happened in France. And if you go and visit the Eiffel Tower in Paris, maybe you did already, you will note that there's a band running around the Eiffel Tower with names on it. So this was a world exposition which heralded the contributions of French scientists who contributed, many of them, to thermodynamics. So you have names like Carnot on this, you have Poisson, you have Le Chatelier. You have Lagrange. You have Clapeyron. Ampere. I mean, it's not exclusively thermodynamics, but it's quite a list of names, right? So if you ever feel like celebrating science while vacationing in Paris, you could always go and check it out. Now, to wrap up today's lecture, these are the two flaws of thermodynamics. The first one is the inherent nature of the postulates. It's only conceptual. I put this in quotation mark because it's still incredibly powerful, right? But it's only conceptual. Definition, which is sort of top down. It doesn't know about atoms. It doesn't know the differences of the materials, right? It's based on observations. And this means heavily empirical. Okay. So expansion coefficients, coefficients in your equations of states, and so on, they are all parameterized for every material. That's a disaster, right? Do you know how many different materials there could be? Have you thought about this? It's outrageous. So just for organic chemistry, some people think there's more than 10 to the 60 molecules you could make up in organic chemistry. We are not talking crystals yet, inorganic stuff and so on. 10 to the 60. Before I mentioned we have only 10 to the 55 atoms in this galaxy. This means we do not have enough atoms to make a hard drive to store just the list of the molecules you could make. Now, if you want to parameterize every molecule with to do thermodynamics on it, forget about it, right? So that's the problem. Of course, if you deal in your life only with 3 different molecules, okay, you can parameterize it. You can, if you want to build a factory and you just want to sell this one molecule, sure, you can parameterize it, easy peasy. But is that the best molecule? Did you really understand what chemistry is about? Right? So extremely empirical, very unsatisfying. Second, we are completely ignoring the revolution of quantum mechanics. So some more extreme variants of scientists in my field would call for the abolition of thermodynamics, right? We shouldn't have thermodynamics in the curriculum anymore. It's ignoring quantum mechanics, right? We do not study the Bohr model of the atom because we don't care. It's wrong, or it's falls short, right? We should be focusing on our most current view on things. So QM is not present, and so there is no first principles, or we also call this ab initio in Latin, if you want to be fancy, prediction of properties. Any questions? That's it for today. I'll see you on Thursday. Thank you.